was start by an integral. That's really hard to carry out. And now we are almost done, but the following analysis was delayed. So in my talk, I will present what we have right now, how we derive the matching coefficient, how we implement the nonperturbative renormalization on lattice. And I also show some figures, but those figures are the figures from previous calculations of the helicity and transversity distributions by LP3 and MC. Okay, so in my talk, I will first briefly go over the large momentum effective theory and show you what the systematic procedures are to calculate Parton physics in general, and then present some recent calculations, including the helicity, the Parton distribution, and the transversity distribution. And in the second part, I will focus on the derivation of the factorization formula for the quasi-GPD, basically using an operator product expansion for the off-forward case, and derive the correct form of the matching coefficient, which turns out to be non-trivial according to our previous studies. And finally, I will describe the procedure of implementing a nonperturbative renormalization of GPD on lattice, and how to calculate the matching coefficient that will extract GPD from the GPD in this nonperturbative RMO scheme. So we have a strong motivation to calculate Parton physics because at the next frontiers of QCD, the electron ion collider will try to probe a lot of Parton physics, including the Luang distributions, OX physics, the C quark distributions, the nucleon spin structure, and especially make a precise 3D tomography of the nucleus that will require us to understand the TMDs, GPDs, as well as Wigner distributions or GDMDs. So a lattice calculation of this kind of physics is both timely and necessary because the lattice might be able to provide information on kinematic regions and the flavor structures like the C distributions that are not so available at current experiments. And the lattice results on the GPDs or TMDs could provide useful information for us to constrain the ansatz used for the global analysis of these quantities. And we can anticipate that in the ESE era, there will be a lot of interplay between theory and experiment. So, so in recent years, the large momentum effective theory proposed by G has been under a lot of development, and it is a systematic approach for us to calculate Parton physics, which is defined on black cone from an Euclidean lattice. So in this approach, we try to calculate the Parton distributions that are usually defined as matrix elements of black cone correlation operators, which are not readily calculable on the Euclidean lattice. So in the Lamet approach, we can construct a time-independent quasi-observable, which is always equal time, so it can be directly calculated on the lattice. And we calculate its matrix element in a large momentum nucleon state. According to a large momentum factorization formula, we will be able to match this quasi-observable to a desired Parton observable systematically with a power expansion. At leading power, it has a factorization form as a matching coefficient convoluted with the Parton observable, and there are inherently power corrections that have also been mentioned by Lattice in his first talk. So, so since this quasi-observable can be directly calculated on the lattice, we can then use Lamet to extract the Parton observable from it. So let's take the example of collinear Parton distributions. If we look at the unpolarized quark PDF, it is defined as a correlation of the quark fields along the light cone with a Wilson line, light cone Wilson line that makes this definition gauge invariant. In Lamette, we construct a quasi-Parton distribution in the spatial z direction, which is in the same direction as the momentum of the nucleus. So, so one can see that if we first boost this operator to the light cone, it will to the large momentum frame, it will approach the light cone, and in the infinite momentum boost, it will reduce to the light cone direction. But this kind of limit cannot be taken in quantum field theory. Instead, we can only calculate this quasi-distribution on a lattice with finite nuclear momentum, which is much smaller than the UV cutoff of this lattice theory. And the Lamette allows us to relate this quasi-PDF to the light cone PDF through a factorization formula. So before we write down from the factorization formula and have a well-defined convolution of the integral, we actually need to renormalize this quasi-Parton distribution on the lattice and perform the continuum limit. So suppose that this quasi-Parton distribution is renormalized in a particular scheme at scale nu tilde. Then Lamette allows us to have this factorization formula. Here at leading power, we can see that this quasi-observable, quasi-PDF is factorized into this matching coefficient convoluted with the light cone PDF up to power corrections. So here we have the IJ and R flavor indices. And this matching coefficient only depends on the ultraviolet scales between these two observables. When the nuclear momentum PZ is finite, then we have to include these power corrections as our systematic uncertainties. So for a long time, it's known how to do the mass corrections, but for the intrinsic hierarchies corrections, is actually not included in the lattice analysis so far. So this morning we learned that we cannot naively think of the hierarchies corrections as powers of lambda QCD or PZ, but actually it will have dependence on x squared, inverse of x squared times minus x. So that will also tell us how reliable a typical lattice calculation is regarding the range of the x.
This is actually related to your result.
Yes.
That this the characteristic scale view has to be y times pz.
Okay.
It's the same, just exactly the same thing. This is your observation that there must be a y there.
Okay. All right. So before we just look at back to the formalism. Ideally, a procedure for carrying out a calculation in Lamette can be divided into 4 steps. First of all, we simulate the lattice matrix element of the bare quasi-PDF, and then perform a renormalization on the lattice. And usually, it is desired to perform this non-perturbative renormalization so that we can have a well-defined continuum limit to extract the physical results. Another reason for us to choose non-perturbative renormalization is because this quasi-PDF will have linear power divergence in it. If we don't renormalize it on lattice, then the matching coefficient has to take care of this power divergence. But since this matching coefficient is always calculated at fixed order in perturbation theory, you can actually cannot eliminate all those power divergence by doing this matching. So you will not be able to have a well-defined continuum limit with a fixed order matching. Yes.
Power divergences are related to the breaking of rotational invariance.
The power divergence is related to the self-energy of the Wilson line. It exists in any theory with a hard UV cutoff, even though it's invariant.
But I'm trying to understand. It's not specific to the lattice regularization. It also appears in the continuum.
In a continuum, it's up to your renormalization scheme. If you work in the NS bar, actually this power level.
You can do the calculation with a finite cutoff in the continuum.
Yes,
so
yes.
And you finite cutoff
you still will have
in momenta.
Yes. You still have it.
Dimensional regularization might hide it because
right.
It sets certain power diversion integrals to zero implicitly just because it assumes rotational invariance.
But if you think of a simple an operator to define quasi-PDF is not restricted. It does not have fixed spin. So the algebraic behavior controlled by dimension. Dimension operator on the E spin.
This is this standard question, so why cannot you define the whole mass of the quark non-perturbative? That is the that's the same, exactly the same question.
Yes. So after this non-perturbative renormalization in this particular scheme, actually is the RMOM scheme that has been studied or carried out in the two lattice papers last year. And then we can take the continuum limit. Of course, if you want to obtain physical results, you should also consider the infinite volume limit. So far, no continuum limit has been taken in the available lattice calculations, but this will definitely be a direction to work on. And then we should subtract the mass corrections and hierarchies corrections. So far, only mass corrections are known how to subtract, but we don't have a systematic way to subtract these hierarchies corrections yet. And eventually, we apply this perturbative matching to obtain the PDF. So in our most up-to-date calculations, we actually have systematically considered all the uncertainties from the first and the third and the mass correction and the perturbative matching procedures. It is the higher intrinsic hierarchies corrections that we have not constrained in our analysis so far.
Okay. Just to understand the hierarchy of scales in when you do the renormalization,
yes,
you do a calculation with an ultraviolet cutoff which is much larger than PZ.
Right.
Yeah.
Right.
Okay. And then you have, say, this power divergence in this ultraviolet cutoff, you remove it by renormalization.
Right.
By renormalization.
Yes.
And then you take PZ be large.
Yes. Large, but compared to the soft scales. Okay. So so far, the Lamet approach has been applied to the calculation of total gluon helicity contribution to the proton spin, and a ton of Parton distributions, mainly for the isovector cases, as well as the meson distribution amplitudes of the proton. Oh, sorry, pion. Typo here. Yeah, I was just copying this. And also the pion PDF. So it is not until this spring that our calculations for the quark PDFs of the proton for the isovector case that actually begin to converge or move closer to the phenomenological results. And here I choose to first display the calculation of the isovector quark helicity PDF. So on the left panel is a calculation done by the ETMC collaboration at a finite spacing and higher mass with a nuclear momentum of about 1.4 GeV. And they match the final result to NS bar scale 2 GeV. So Andreas just displayed the case for the unpolarized distribution. Here is the result for the polarized distribution. On the right-hand side panel, this is the result by the LP3 collaboration that I belong to, and we did a calculation on a different lattice ensemble, also at a physical pair mass, but with nuclear momentum as large as 3 GeV. and we match the final result to 3 GeV. So if we, firstly, if we look at the ETMC result, when they gradually increase their nuclear momentum, we can observe that their curves are gradually moving close to the phenomenological PDF in the range of x, maybe 0.1 to an intermediate range. And this is also agrees with our discovery that our results agrees quite well with the NNPDF and the JAM analysis in this finite range of x. But there's still discrepancy at small x, which is what we cannot control, as well as the large x, that is x close to 1. So because we didn't make a logarithmic plot, it's not very easy to tell the actual difference between our large x behavior and the global analysis. But we shouldn't be too optimistic about the prediction in this range.
But the new analysis, so in principle, of course, A times PZ is 1.5, yes? So
yes.
What can ask questions?
So, so far, one way to estimate this discretization error is to vary the nuclear momentum and
the special relation.
Yeah. Okay. So here I also want to make a further comment that for the development of any approach, you first start with a formalism that works for the ideal case, and then you start considering the systematic corrections in this approach. If there's any, and then you will find the limitations, but you can still find places where you can make improvement. So far, what we have observed now is we can have a fairly nice result in the finite range of x, maybe from 0.1 to 0.6 or 0.7, and we can actually gradually improve it by having larger statistics and more steady state analysis. But to make our results more predictive in smaller x range and larger x range, it does not only require us to go to higher nuclear momentum, but also require the series to understand better about how we can quantify these hierarchies corrections. So maybe this will motivate us to get involved of those kind of studies.
Just one comment. I mean, how you plot the results. As we said earlier, the say phenomenologists usually work with the valence and the C-quark distribution,
right?
And the polarized valence distribution is actually very well constrained.
Yes.
So since you have your correlator at positive x and negative x,
yes,
you could also plot separately the valence and the C distribution.
If you flip this and this to the positive range, then you will.
What I'm saying is there's a big uncertainty in delta U bar minus delta D bar in the parameterization. By the way you plot it, you have this uncertainty both in the on the left side and on the right side.
Right.
So it makes the phenomenological extraction look worse than it actually is. So if you compare valence and C, then you would probably see that in the valence you have a very significant deviation from phenomenological extraction, and then in the C it's all over the place.
Yes. Okay.
In the lattice calculation, do you have the C-quark configuration?
The C-quark is included in
yes, the correlator is negative x.
No, but when
This doesn't. But another question is how he calculates that correlator. But in principle, the polarized anti-quark distribution is given by the value of that correlator at negative x.
But they don't have probably this point disconnected contribution.
But it's
No, we
isolated.
don't.
This
It's
is
isolated.
It's isolated.
Yeah, so
We can only probe the flavor asymmetry in the
It's
CH.
less.
Yeah, so we want to be more predictive about the flavor asymmetry in the C distributions. So far, the two collaborations have a quite apparent discrepancy in for the C quark distributions. We have our results indicates that the C quark asymmetry is very small and maybe consistent with 0. But ETMC's result still have a large oscillation.
why don't you compare your data? Because it's in coordinate space.
Yes.
Because this is, it involves already some manipulation, some assumption. But you have just data in coordinate space. So why just put that data across your data?
If I remember correctly, the two collaborations have data as a function of Z separation.
Yes.
Yes.
Yeah.
Yeah,
They
so
are
this,
pretty much consistent.
So
yes, so then what happens?
okay, so as far as I understand, the way they calculate the bare Newton matrix element, they give more smearing of the gauge link than we do, and then after the nonperturbative renormalization, the way they still have different smearing than we do. So what we can compare is the renormalized Newton matrix element in the coordinate space, and then we have different parameters. Their calculation is at 1.4 GeV, but our calculation is at 3.0 GeV. So unfortunately, we haven't tuned our parameters to be the same to compare our.
Can you compare the raw data before renormalization?
The raw data cannot compare because they did a lot of smearing to the gauge links.
But it should not matter, because in those cases you assume that, okay, you have the data that you have, but you assume that it's some approximation of continuum limit data.
Okay.
And it's a question of how you plot it. You shouldn't plot it as a function of Z, but a function of Z. It's a invariant variable. It's
Okay.
a invariant variable, and then, okay, you also see this.
That's a good point.
Yeah, and then, okay, I don't know, but this is a way to compare the data, because then otherwise there is something inside, and then this will completely agree.
Well,
Because in those cases you assume that this data kind of with approximation to reality, you know better. Yes? But then they have to be compared as in a reasonable way. So this is a function of Z and PZ, because invariant variable is PZ, P times Z.
So for the bare matrix elements, yes, we have to have compared our plots. Qualitatively, we are different in the range of Z equals 8 times of line spacing,
For large distances.
for large distance, and we suspect that is because they applied more smearing to the gauge links. We only applied one heap smearing to the gauge link, but they did 5 times or 10 or even more, and that would affect the UV divergence in the bare matrix element. So that's why I don't think it's meaningful to compare the bare matrix element.
Yeah, the bare matrix, I don't know, but after you do what you think is the conversation, they also do it, then you come to some quantities which are physical quantities in principle. So they should be possible to compare after factorization. And then, yeah. So this is interesting thing.
Okay. So so another figure I want to display is the lattice calculation of the isovector quark transversity distribution. So ETMC published their result first. So the blue band is their prediction for the isovector distribution, and the gray band is from the JAM analysis earlier this year, and this pink or purple band is the JM analysis combined with the lattice input of the calculation of the tensor charge. So it's actually not surprising to see the lattice calculation using the quasi-PDF approach to have this kind of uncertainty. But it's very interesting to see that it actually agrees quite well with the global analysis plus the combined analysis of data and the lattice result of tensor charge.
I mean, if you compare the CDs and CDs plus tensor charge from the lattice, you see this enormous improvement. It just means you 100% rely on the shape of your parameterization. Because the only new information you throw in is one number, which is the integral.
Yes.
And if that improves the value of the fit uniformly several times across X, it just means you rely on the parameterization.
You have to take into account that your parameterization is very flexible. It's not just. Well, in grade school, we have to try unbiased neural networks.
Yeah.
But I don't think it's just because of the shape. Oh, let's make that feeling.
Yeah.
I cannot prove it right now. I think it is. Because it's what you say is that you might find different shapes that will give you the same.
Actually, I mean, if you give me the gray band, I can find plenty of shapes that.
But if you think like how this fit was done, is that GT was just 1 point. It's 1 point. It's like what Krasner was saying is it's difficult to understand how to add constraints on the integrated quantities. And here we just took this integral and we added 1 point into our high square. This is what type of movement we found. It's not the bulletproof thing. It's just one step. How Lattice can help. In principle, of course, yes, we need to be as flexible as possible for all these types of shapes. For instance, you see something which looks like an artifact on your side. Who knows?
All right. So the LP3 collaboration also has a same calculation. We actually are consistent with the ETMC calculation as well as the JAM analysis. But on the C quark side, we have our result is actually very consistent with 0. The difference between the ETMC result and the LP3 result is probably due to how we take the Fourier transform. So this kind of oscillation could be from the Fourier transform within a truncated region. But if we Fourier transform the derivative with an assumption on the derivative beyond the truncation point, we actually get a smoother curve here. So that's the status of the transversity calculation.
If I may ask, but in this Alexander and others paper, they do find the contribution from C quarks, but also time. So,
also time.
Yeah, I guess so. So it might not be surprising that we find something.
Yes.
This is actually predicted 20 years ago in the Cairo solid group model, where it comes out in an almost model independent way. It's really a consequence of the chiral structure of the effective interactions.
Okay, so then we are naturally motivated to calculate the GPD from the large momentum effective theory. So the following parts of my talk will focus on the factorization and the matching calculation for this quasi-GPD observable. And it might be a little bit too theoretical and formal, but I hope it would be interesting to the audience. So to construct the compared to the unpolarized GPD, we can construct our quasi-GPD in a way similar to to the quasi-PDF. The skewness parameter is defined by the difference in the longitudinal momentum. But in the large momentum limit, it will be the light cone skewness plus a mass correction. And so here we regard it as a very small correction. Then following the quasi-PDF study, we can anticipate that a renormalized quasi-GPD can be factorized according to this convolutional form. So the matching coefficient will depend on the UV scales in the quasi and light cone observables, but it will also have dependence on the skewness parameter. So in the transverse momentum cutoff regularization scheme, this one matching coefficient was already calculated for the bare quasi-GPD and GPD, renormalized GPD. But the form of this matching coefficient was just assumed to be true, and there's no rigorous derivation of why the functional dependence of this matching coefficient over these variables are like this. And it was not until recently that we find out that the logarithm of mu over the momentum must be the logarithm of mu over the Parton momentum. So there's a non-trivial factor of the Parton momentum fraction y in the logarithm of this variable. And therefore, to take a cautious approach, we will try to derive this factorization formula following the similar approach that we did earlier for the PDF case, and determine the functional dependence of this matching coefficient. On the other hand, we cannot use the matching coefficient for the transverse momentum cutoff regularization scheme for the lattice calculations, because on lattice we want to do a nonperturbative renormalization. So we still need to calculate the matching coefficient for the GPD case. Okay, so how to derive this factorization formula? We use the textbook OPE approach. So first, we start from this local bilinear operator that is used to define both the quasi-PDF and quasi-GPD. The quasi-PDF is in the forward case, and the quasi-GPD is in the non-forward or forward case. And it's already known that in the coordinate space, this bilinear operator can be multiplicatively renormalized up to an exponential factor, which will subtract all the linear power divergences and the logarithmic divergences in this multiplicative factor z. So if we renormalize our bilinear operator in the MA spark scheme, then we can consider an Euclidean operator product extension for this non-local operator. So we already know that for the forward case, we can expand this in terms of local gauge variant operators, and we can write it in the twist basis. So at the leading twist, we will have a tower of twist to quark operators and a tower of twist to gluonic operators. Here, the vector E is along the z direction. So if we consider the isovector case, we can neglect the gluonic operators and focus on the twist to quark operators. This form has already been used to prove the factorization formula for the quasi-PDF by Jian Wei and Yan Qing, as well as earlier this year. So when we apply the OPE to the off-forward case, we have to consider the mixing of these local twist to operators with this, other twist to operators with total derivatives. So it is known that under renormalization, this operator can mix with a tower of operators of the same dimension and of twist 2, but with a finite number of total derivatives, and it is known that this mixing matrix is a upper triangle matrix. So at leading log, this mixing matrix can be diagonalized by choosing conformal operators by choosing the conformal operators. And for the leading eigenvalue and the leading eigenvector, this conformal operator can be written as in this form. So here, Cn3 is just a Geigenbauer polynomial, and if we combine the nth power of partial total derivative from this here to this Geigenbauer polynomial, this whole operator is just an operator combined that includes partial total derivative and left-right derivative as a homogeneous polynomials. All right. So
what are the symbols in the numerator and denominator of that?
Here is the covariant derivative to the right minus the covariant derivative to the left. And here is the partial derivative to the right plus the partial derivative to the left.
Okay, so which includes both total and covariant.
Yes,
yeah, okay.
Yes. Okay, so, but this is only at a leading log accuracy. If we go to higher orders of LS and the LS times logs, the diagonalization will be different. But since this mixing matrix is always an upper triangle matrix, we can always diagonalize it. And we can write the eigenvectors in a more general form, except that, which is similar to the conformal operator, except that here, this polynomial may not be a Geigenbauer polynomial. So with this diagonalized mixing matrix in mind, we can re-express the OPE for the quark bilinear operators in terms of these eigenvector operators. Here we just add a new sub-series in this OPE expansion. So the leading vector has a coefficient of 1, and it must include this forward operator, this operator that exists in the forward case. But so far, we are not sure if the other eigenvectors should be included in the series expansion. But if they exist, they can only be of higher orders. But after all, the inclusion of the other eigenvector operators will not affect the conclusion of our derivation. So with this re-expressed OPE, we can evaluate the matrix element of this non-local operator in a large momentum nucleon state. So when we put these eigenvector operators into the nucleon state, they can be given by the special moments of the Lattice GPD times this traceless kinematic factor. So here, this moment, which mimics the Geigenbauer moment of GPD, is given by integrating over this y of this GPD weighted by this polynomial times the c to the nth power. So as we can see, if the longitudinal momentum of the average momentum Pz, which is E dot P bar, is large, then we can neglect these trace terms, and then we can plug in these matrix elements of the local operators back into our OPE, and then have this form. So this is the large momentum expansion of the matrix element of this non-local operator in the coordinate space. The next thing we do is to Fourier transform this non-local operator matrix element into the X space to get the quasi-GPD. So the following is purely mathematical. So one way to do the Fourier transform is we can combine the c to the nth power into our product of z times PZ. And then we find out that after we sum over M and N and do the Fourier transform, the matching coefficient will be a function of y over c, but also x over c because we rescaled the integration variable z. And it also will depend on mu square over c square times pz square. So eventually, the factorization formula will take this form. This is actually very similar to the evolution equation of GPD with this evolution kernel, except that we have a non-trivial dependence on the logarithm of mu square over c square times pz square. On the other hand, since this polynomial c and n is a homogeneous polynomial, the combination c to the nth power times this polynomial can be rewritten as y to the nth power times a polynomial of the inverse of this variable. So by redoing this shuffling, we can derive that the quasi-GPD can be factorized into a form of a function of x over y and the c over y and the mu square over y square times pz square. And this looks more similar to the PDF, the quasi-PDF factorization formula that we have derived previously.
Let me make a comment.
Yes.
So what you're doing actually is called conformal operator. And there is a more strong statement. That, so this what I can say that this coefficient function is here can be expressed in terms of the forward coefficient function. So you have calculated the forward coefficient function, and this you need to define this coefficient.
Okay.
You need to do a second calculation.
Okay.
So if you look at our paper with Dieter Müller, this one, we did it for a slightly simpler situation where I have 0 and the pi. Kinematics is slightly different, but the operator structure is of course the same. We also have a forward. But this is technique was developed actually by Dieter Müller, is related with exactly for the renormalization of the GPDs. So this is called conformal operator for the expansion and so on. In principle, we can even do this maybe for 3 loops now.
Yes. Okay.
So this is the essential principle statement that the C is actually can be determined from the forward case. From the forward case.
From the forward case.
From the forward case, yeah. Up to starting.
It's not trivial to determine the c dependence in the C.
It is close. It is, but it is called the conformal operator.
Okay. Thanks. Yeah. All right. So these two forms are in principle equivalent to each other, and they have both appeared in the literature for the evolution equation of the, GPDs, except for the dependence on this non-trivial logarithm of this variable. So, to check our previous study of GPD, PDF, and the distribution amplitude, we can actually take the certain kinematic limit of this factorization formula. So if we want to check the factorization formula for the distribution amplitude, we can take the limit of c equals to 1. And using this form, the factorization formula must be a function of x and y and mu square of the nuclear momentum pz squared, convoluted with the light cone distribution amplitude. This form was used in the reference that calculated the one we mentioned before, but they didn't actually prove it. So on the other hand, in the forward limit, we can take c equals to 0. So using the second form, we will naturally reduce to the factorization formula for the collinear PDF that we have derived before. Okay, so so this is the factorization formula for the quasi-GPD. And next, I want to discuss how to renormalize them non-perturbatively on the lattice and then match to the MS bar GPD. So since the renormalization of the operator does not depend on the external state, so the whole renormalization program for the quasi-PDF can be applied to the renormalization for the quasi-GPD. And according to our previous study for the quasi-PDF renormalization, we carry out this renormalization in the regularization independent momentum subtraction scheme. That is, we determine the renormalization factor Z in the coordinate space by imposing a momentum subtraction condition in a quark state that is far off shell. So the renormalization condition is simple. It requires that the renormalization factor multiplied by the bare matrix element must be equal to the tree level matrix element at a given subtraction scale mu r and the nuclear momentum pzr and quark momentum pzr. Then we can calculate this bare matrix element non-perturbative on the lattice, and then derive this non-perturbative renormalization factor. After we obtain this non-perturbative renormalization factor on the lattice, we can then use it to renormalize the nuclear matrix element of the quasi-GPD. After we perform this renormalization, we should be able to take the continuum limit and obtain the RI norm scheme quasi-GPD that is to be used to match to the MS bar GPD. Since this renormalization scheme is independent of the UV regulator, we can actually carry out the matching coefficient in a dimensional regularization scheme, just like what we did for the quasi-PDF case. So our whole program of calculating the matching coefficient for the RMOM quasi-GPD is done with dimensional regularization. As a first step, we need to calculate the one loop renormalization factor with dimensional regularization, and it is given by this simple formula. So here at tree level, it's just 1. At order Fs, it is given by the one loop correction to the quark quasi-PDF. So here there are 2 terms that contributes to Z. This comes from the real diagrams associated to the one loop correction to the quark quasi-PDF, and this 1 corresponds to the virtual diagrams. And if we take Z goes to 0 at finite epsilon, the one loop correction will be 0, guarantee the vector current conservation. And the next, we need to obtain the matching between the bare quasi-GPD and the MS bar GPD. And this matching calculation can be done in an on-shell quark state, so that we can identify the IR divergences in the quasi-GPD and the MS bar GPD. And for this bare quasi-GPD calculated in this on-shell quark state, we will use this renormalization factor to renormalize it. So eventually, if we calculate the one loop correction to this bare quasi-GPD within red, we apply this RMOM renormalization constant. This will be the renormalized quasi-GPD. And knowing that the bare quasi-GPD is related to the bare matrix element of this non-local operator is related to the Fourier transform of the bare of the MSR quasi-GPD. We can plug in, and the factorization of this MSR quasi-GPD into the light cone MSR GPD. We can plug in the relation back into this equation and eventually perform a Fourier transform to obtain the matching between the RMOM quasi-GPD and MS bar GPD. So finally, we will obtain the matching coefficient for the non-perturbative renormalized quasi-GPD, and it is given by the MS bar matching coefficient minus these counter terms from the RMOM scheme. So this result and along with this are already calculated in literature. So what we need to do is just to compute the matching between the bare quasi-GPD in the MS bar scheme and the light cone GPD, which can be done easily with dimensional regularization with an on-shell quark state. So currently we are trying to complete the calculations of this term, and then eventually we will use this result to extract the GPD from the lattice renormalized quasi-GPDs. So if we apply this matching, in principle, it is supposed to cancel out all the dependence on these intermediate scales, PZR, mu r, as well as the nuclear momentum PZ, up to those power corrections. But in practice, since our matching is only calculated at one loop order, we will still have remnant dependence on these intermediate scales, and they should be considered as higher order effects. Since we also calculate only at single lattice spacing, there could also be lattice discretization effects that's combined with PZR times A and mu r times A. On the other hand, although the matching coefficient in the transverse momentum scheme is not very helpful for lattice calculations, but it will serve as a cross-check for our MS bar matching between the quasi-GPD and the GPD, and that will be helpful in our calculation. That's the status of our GPD calculation so far. By my estimate, we will finish the calculation of this matching coefficient within next week, and then we can use this to analyze the available pion quasi-GPD data from our lattice collaborators. So hopefully, you guys can see our publication within 1 month or 2. I can't guarantee. No, I don't know how good it is. Maybe it's very ugly, but we will have something to talk about next scenario. So let me summarize. So first of all, we use OPE to rigorously derive the factorization formula for the quasi-GPD, which is kind of trivial considering all the existing works we have done before. And then we can perform the renormalization for the quasi-GPD the same way as for the quasi-PDF case, which saves a lot of work. And eventually, we are close to finishing the perturbative calculation of the matching coefficient for this RMO quasi-GPD. So that's all from the talk. Thank you.
Questions? So as I say, this factorization procedure, there's no forward factorization procedure. It's the formal operator, but it's actually implemented in the analysis code that I think, for example, this is just implemented. The only difference here is that you will use different coefficient functions because they have to follow the process. They have creation functions to vector kinds. You will have this works with the Wilson line, so of course coefficient functions are different.
Yes.
But forward I know. That was a big simplification because this analysis that they have now in NLO, in principle, can be advanced to NLO because this two-loop calculation for the correlation function to vector kinds is known. Actually, it was 3 loops known. But this is something else. And just a small remark that on the way, Lamet essentially disappeared. It just do your calculation in MS. That's it.
We just need to do a calculation in this part.
Yeah, so Lamet is some intermediate factorization scheme, which you can use if you like it, but at the end, you know, with your technical calculations, this is this.
Okay.
That's what we do. You do all the calculation MS bar, and we don't mention Lamet. We don't need it.
But when we calculate this function, you have there exists results in literature that we can use to derive it. That's what you want to.
When I say that you can just calculate it in MS bar, just calculate it.
Oh, calculating MS bar is also part of Lamet, so I don't know what.
Yeah. This is a part of it. Okay. But what I say that you just this is standard calculation, which you normally do it in domestic, calculating coefficient functions. We don't call it Lamet, but it's the same thing. You don't need to do this. Lamet is some particular factorization scheme.
And also, MS bar we define PDF in MS bar class QCD.
Yes, you want.
So you already know that part is sensitive to how you normalize the PDF, non-PDF response. In principle, for the quasi PDF or whatever, the left-hand side of calculation, you can normalize anything you want.
Right.
You don't have to normalize it.
MS5 is the easiest for adaptive calculations. You can go on shell with massive class. That saves a lot of.
Let's say it's a one choice.
One choice, yes. But it's not the only choice. We are taking the easiest path to obtain this final result.
Yeah, but you eventually want to have Parton distribution in MS5. But in this sense, it is natural to do population dimension.
Sure, you
Otherwise,
can
you
do
will
both
have
sides and that's fine. But the required is the right-hand side.
Yeah.
Yes.
But my impression actually is, of course, at this level of one-loop calculation, you can't have explicit results for your coefficient functions in the function of this PZ. But if you will go to higher loops, so my prediction is that if you stay at the level of coordinate space functions, the results will be expressed in terms of well-understood functions. But this last Fourier transform will be very, very non-trivial, and I'm not so sure it's worthwhile to do it analytically because you can get even in one loop, you will get quite some.
And if we can impose vector current conservation, we don't have to worry about the part proportional to delta 1 minus x.
But still, you will have just this Fourier transform of this function in two loops that would be really hassle. You better not do it.
Depends on the operator. Sometimes if you don't have certain analyticity, you don't have a moment, and for a transfer, you have all kinds of troubles.
Right.
That's why I think I like what you say. It's a match. You don't have to do momentum, so you get direct match coordinate space calculation to the PDF for the PDF in momentum space. So in that case, you can avoid a lot of reverse controls.
And in coordinate space, there is also explicit formula tells you that the forward coefficient function is enough, eventually up to some terms proportional to the QCD beta function. This is implemented in PDF in GPD in two-loop GPD evolution.
I think the reason we want to go to momentum space is because we have so much correlation data in coordinate space. Even though at large distance, the hierarchies corrections are there, but after we perform a Fourier transform, in large momentum, we'll just screen out those long distance correlation. But because we have many data points, you can obtain a relatively smooth curve in the X space for you to do the matching. So that's one of the I wouldn't say advantage, but in practice it helps for to facilitate.
Those data have a tremendous correction.
I think this is a non-trivial and interesting question because they have this data and we stay at distances z 0.5 Fermi. They actually go to large z. Include all this data, which would be suppressed by large momentum, but still they give some contribution. The question is how reliable this contribution is. As first sight, it cannot be reliable because you just did. But on the other hand, we know that in some cases it's better to integrate, for all phase space, and it's usually because of unitarity. You can deform the integration quantity and so on. And but here this quantity distribution, they don't have good analytic properties in this momentum. So it's a little bit studied, but that's a situation. But analytical things are how to argue that if you integrate over these large distances, you still have some reasonable estimate of the term that you don't know. This is actually an interesting question.
It's a quantitative issue.
Yeah, no, okay. I can tell a little bit more what I mean, but this is related to basically duality in some sense. This is when you say that we calculate the gluon on match. So what do you actually mean? You mean that in reality you can deform the integration quantum in such a way that the results actually large. And in this case, I'm not sure because we don't have analyticity.
Analysis is
And that's crucial, yeah. This is crucial. And here I don't know, but I also cannot say that it's just, it's an interesting question.
At their level, you should have analyticity before you do MSR or any renormalization.
No, I mean analyticity in the complex PZ plane.
Yes, when epsilon is finite. At
Is
the
that
com, in the
No, already for the regularized function. It's a physical observable.
okay.
The question, what the analytic properties occurs as a function of PZ. I'm afraid it's not very.
We actually give example in the 2018 paper. We did the Fourier transform in many space. It's the price tremendous for a certain.
So if you have analyticity, you can deform the integration contours away from singularities, and that's so. But you don't know.
That was part of the reason it took me over 2 years with an intention to prove the renormalizability for distribution. We initially worked in momentum space, and momentum space, when the moment is large, does not guarantee the operator the local position space. So if you have on the power dependence, okay, but if you have large dependence, then you have trouble.
Mm-hmm. Yeah.
And then we give up. We didn't make position space on the match.
Yeah, I don't know how to. Actually, I don't know how to approach this analyticity problem at present. So, when we derive this matching coefficient, we computed the matrix elements of these non-local operators, not from the moments. So it seems that at least at one loop, everything agrees with what we have expected from this factorization formula. So
no, it's just analytic inclination for moments as usual, but this is a bit different. But in present, it's just a question whether your expressions remain finite, if you wish. So where you have singularities. The complex is probably in coordinate space the function looks good and you understand how it looks. So you make a Fourier transform, so the question is where it can have singularities. That's probably it should be not very difficult to see, but I'm afraid that this analyticity will be not there. And that will be the problem. In the usual sense.
We'll talk later.
Yeah.
We actually gave an example of singularity.
Yeah.
okay.
So usually we have some cut and we imagine a part of this cut has some physical meaning and so on. And this is.
Questions? So we have the lunch break now, and then in the afternoon we have a time for a global discussion. What we want to communicate as the results of this meeting, and particularly what of the items we discussed are relevant for the EIC program, possibly be say forwarded from here.